Welcome again.
Yes, thank you again. And I'll talk about now practical asynchronous distributed key generation protocol. This is joint work with Tom, Zhuolun, Andrew, and Ling from UIUC and Lefteris from IST Austria. So this is kind of related to the previous talk as well. But this is the brief outline of my talk. I'll first define the problem statement and give some background. It'll be a nice overview of consensus in general. And I'll briefly talk about summary of results, the main ideas, and the evaluation, and also some open problems. Awesome, let's get started. So asynchronous distributed key generation, or ADKG, is this problem which is parameterized by n, t, and l. As you might have guessed, n is the total number of nodes, and t is the maximum number of faulty nodes. Here we assume that t is up to 1/3, and l is the reconstruction threshold of a secret. I'll explain what it is. So this is the protocol among n nodes where up to 1/3 of the nodes could be malicious, such that at the end of the protocol, every node outputs a common public key. Every node outputs a common public key pk and a secret share. We have seen some secret sharing, a secret share of the secret z. So every node does that. They have a common public key, but they have an individual share. We want to bootstrap such systems where GIs are n, l threshold secret share of the secret z. Our system model for this paper is this. We consider asynchronous systems where network bounds could be unbounded, but messages will eventually get delivered. This is slightly more robust model than partial synchrony. And we have setup in terms of setup requirements, we again assume public key infrastructure and common random string. So asynchronous DKG has, or in DKG in general, has many applications. First is threshold signatures. They are used in lots of efficiency reasons in consensus algorithm like state machine applications. They are also used in threshold wallets. They can be used to bootstrap threshold encryption system and also randomness beacon. We have seen there are many applications of randomness beacon as well. I want to mention the CKS05 example we have seen actually assumes DKG and then they do the rest of the thing. So I'll talk about a background. So we have seen threshold secret sharing in the last talk, so I'll not go into this. We have also seen verifiable secret sharing. What we need in this paper is something called asynchronous complete secret sharing, which is asynchronous variant of verifiable secret sharing with some extra properties. For this talk, we don't have to know the exact differences, but you can think of that as asynchronous variant of verifiable secret sharing. We need some other primitives. One is reliable broadcast. This is one of the classic primitives in asynchronous consensus. And this is defined as follows. So we have a dealer that has a message M, and we want to run a protocol RBC on the message such that every node outputs the message at the end of the protocol. Note that simple schemes where dealers simply multicast a message to everybody won't work in case of malicious dealer, because a malicious dealer may send different message to different nodes and sometimes may not send any message at all. So we want a broadcast primitive which is robust against malicious failures. More formally, RBC requires these properties. Well, first is agreement. It says if two honest node outputs a message, they should output the same message. We also need validity that says if the dealer is honest, then at the end of the broadcast, everybody outputs dealer's message. So intuitively, this is very similar to your first basic notion of broadcast that you can imagine. And you also need totality that says either all honest node outputs or everybody stays undecided. This is slightly weaker than termination, strong termination, where everybody needs to always output. We'll see what that is in the next slides. So you also need asynchronous binary agreement, which is a single bit asynchronous consensus protocol. Pictorially, this is what it looks like. We have 4 nodes here. Everybody has a bit, B1 up to B4. One of the nodes could be malicious. So they run a asynchronous binary agreement protocol or ABA protocol, so that at the end of the ABA protocol, everybody outputs a bit. We again want some properties. First is agreement that says if two honest node outputs a bit, they should output the same bit always. And the validity notion says if all honest nodes started with a common bit, let's say B here, then the ABA protocol should output the same bit B. And the third is termination. It says the AVA will eventually terminate. Doesn't matter what the adversary does, the AVA should always terminate. These are the properties that we want. But for ABA, there is a very classic strong impossibility results that says deterministic consensus, asynchronous consensus, is impossible. So ABA is a single bit consensus. Even this is impossible in deterministic scenarios. The way people get around this is to use a common coin to randomize this protocol so that they can, with a very like a strong probability, the ABA protocol terminates. So this is the existing landscape of asynchronous distributed key generation protocol. The first DKG protocol, which is non-synchronous, was from 2008, which is in partial synchrony. They again have very high communication cost, kappa and n to the fourth, and round complexity is ordered n rounds. Recall, n is the number of parties. There was a recent work at CCS 2019 that is fully asynchronous, but still has the same communication cost. There are a few follow-ups. So last year, they get good communication cost and also good round complexity, but they have this issue where secret key is a group element. This is a subtlety. What this prevents us from using this DKG with off-the-shelf, like a threshold signature scheme, like BLS threshold signature scheme, or those kind of things. So these are not very suitable for applications. So what we want is a general purpose asynchronous DKG. And this is what we get in our paper that has a communication cost of kappa n cube. Kappa, again, is the security parameter. And it takes order log n rounds in expectation, and also, again, assumes DDH, RO, and PKI in the standard CRS model. Note that although we need order log n round in expectation, if the network behaves synchronously, we get order 1 rounds in practice. So our paper says we are practical asynchronous DKG protocol. So I just want to briefly highlight. For example, with 128 nodes, if we want to run DKG, our single-threaded Python implementation takes about 50 seconds. But if we parallelize, we can still get, we'll get much better, I hope. But I still feel there, for certain parameters, if the threshold is high, the scheme still requires a lot of work. So there are a lot of scope for improving the DKG scheme, at least either theoretically and also practically. While designing a DKG, we also designed something called another primitive, which is asynchronous complete secret sharing for random secret. So there are other protocols which have good communication costs, like kappa n squared and order n computation per node. But these works have ACSS, which are not homomorphic, and we crucially use this homomorphism property for our asynchronous DKG. So to get that, we had to design a new asynchronous complete secret sharing protocol that maintains this old communication cost and computation, and also additionally provides homomorphism. To do so, we end up paying, I have to use DCR, decisional composite residuity assumption. We don't know how to get these properties from DDH. And that's a good open problem to work on. So let's now look at how generally DKG constructions work. So this is the general DKG framework. It's same in synchrony, asynchrony, and partial synchrony as well. So what happens is each node samples a random secret and shares it with using a verifiable secret sharing. Every node will do the same. Then what we do is at the end of the secret sharing phase, nodes run a consensus algorithm to decide which VSS terminated correctly. And once they agree on the set of correct VSS, they simply add the corresponding secret, and that's the secret key. And the public key is G to the secret key. And the consensus algorithm has to ensure, I am already one slide ahead. So the consensus algorithm has to ensure that there are at least T plus 1 VSS secrets you are introducing in the random secret, final secret key. As you have seen, we have seen the impossibility result in asynchrony, that deterministic consensus is impossible. And in more detail, what happens is the asynchronous consensus oftentimes depends on common coin. And here, the way we generate common coin, they typically require asynchronous DKG as a trusted set of phase. And here we see that asynchronous DKG indeed depends on requires consensus, so we see a circularity here, and most of the work in asynchronous DKG goes in here, like how do you get this circularity, break this circularity, and this is what I'll focus in most of my talk. So this is our approach in general. So we have n equal to 3t plus 1. We have 4 phases again: sharing, key proposal, agreement, and key derivation. I'll mostly focus on the agreement phase because that's the most interesting part of our protocol. Sharing phase is, as usual, everybody samples a random secret, and they share the random secret using ACSS, Asynchronous Complete Secret Sharing, which has slightly stronger properties than VSS or AVSS. Then this ACSS terminate. We are working in asynchrony, so it might happen that this ACSS instances terminate in different orders at different nodes because we have no bounds on message delays. They might see different order in how this ACSS terminates. Let's say at node 1, ACSS 1 and 3 terminates, node 2, 2 and 3, and node 3, 1 and 3. So they have different view on which ACSS terminated. So this is the sharing phase. Then we have this key proposal phase, which is an extra step that we introduce, where each node then reliably broadcasts the set of ACSS that terminated at that particular node. For example, node 1 will reliably broadcast T1, node 2 will reliably broadcast this set T2, and similarly T3. Then again, due to asynchrony, this reliable broadcast instances may terminate in different order and at different latencies. So what this node does then, they just create a vector now instead of a set of all the RBC instances that terminated at those nodes. For example, node 1 will create this vector T1, T2. That means these two are reliable broadcasts terminated at node 1, and the remaining two are yet to terminate. They're undecided on that. Similarly, node 2 here, RBC2 and RBC3 terminates, so node 2 has these two non-zero non-baud values and other baud values. So this is the key proposal phase in our protocol. Then we go on to the agreement phase. Now, instead of running a single consensus algorithm, we now run in our paper n parallel binary agreement protocols. And here, the ith binary agreement protocol wants to decide whether the ith RBC terminated successfully or not. So since there are total n RBCs, we need n ABAs. In this ABA protocol, a node, this is how a node inputs values. For all RBCs that terminated at that particular node, it inputs 1. So here at node 1, T1 and T2 terminated, so it inputs 1 to ABA1 and ABA2, and it avoids inputting anything to the remaining ABAs. And this is for a technical reason. Similarly, node 2 inputs 1 to ABA2 and ABA3 and does not input anything in the remaining ABAs. Node 3 also does the same. But now I'm cheating, right? We cannot simply run the ABA protocol because we have no way of generating common coin, and we have seen this circularity issues. And this is one thing that you should take away from our talk is how we address this issue. And the main idea is, so we have these TIs sets, which are set of ACSS instances that terminated at that particular node. And if we ensure this ACSS, this set is large, let's say it contains more than T+1 shares, then we use this TIs to generate common coin for that particular ABA. For example, for ABA1, we use this T1 as a source of entropy. Like we use this T1 to generate common coin for ABA1. Similarly, T2 for common coin to generate common coin for ABA2, and same as T3. This is how I address this circularity issue. But there is also one more subtlety. What if there are no TIs for certain I? For example, here for ABA4, the fourth node is malicious, so it did not RBC reliably broadcast anything, so there is no TI for this ABA4. So how will this ABA4 terminate? So this is one thing that we have to address, and we'll come back to this later. Let's say the good ABAs, which are ABA1, 2, and 3, among them ABA2 terminated with 1. Then the node, once one of the ABA terminates with 1, the node inputs 0 to the remaining ABAs. So node 1 now inputs 0 to ABA3 and ABA4. Node 2 and node 3 also does the same. Let's say first 3 ABAs terminated, 2 of them outputted 1 and 1 of them outputs 0. Now we come back to this problem again. There are no TIs for ABA4. How do we ensure this fourth ABA will also terminate? So this is our another important observation. We observe that this is we call good case coin free. And this is the property we observe that this FLP impossibility applies when honest nodes have different inputs. And the subtlety here is that if all honest nodes start with the same input, then an ABA can terminate deterministically without using any common coin. Now let's look at ABA4. Since there are no TIs, all honest node will input 0 to the fourth ABA. As a result, this fourth ABA will deterministically output 0, and hence we can finish this ABA without using any common coin. And this lets us go beyond the fact that there is no TI for the fourth ABA, like T4 for the fourth ABA. This is another subtle, crucial observation of our paper. And finally, we have this key derivation phase where we looked at all the ABAs that terminated with 1 and just take the union or any deterministic function of their key sets and then derive the secret key as, like here, the union set is 1 to 3, so the secret key is S1 plus S2 plus S3, and the public key is H raised to the secret key. So we also implement our protocol. We do a single-threaded Python implementation. This is more of a proof of concept implementation. And we use a Rust implementation for elliptic curve operation. Our implementation supports both curve 25519 and BLS 12381 elliptic curves. We do this because the later supports pairing and BLS threshold signatures uses pairing. So we thought if you want to use our DKG for pairing based signatures, it should support pairing based curves. Our protocol can support any reconstruction threshold from t+1 to n minus t. And a reconstruction threshold of n minus t is very important for efficiency in state machine replication protocols such as hot stuff. We evaluate our protocol using AWS EC2 instances, and our code is public here. Let's look at our evaluations. We have looked at the runtime. With 128 nodes, we can, for low threshold, where the threshold is t+1, we only take about 45 seconds to run an ADKG, but with high threshold, even with 64 node, our runtime, single-threaded runtimes go beyond 150 seconds. We'll see the reason in a slide later. We also measured the bandwidth uses. So with 128 nodes with low threshold, per node bandwidth uses is about 12 megabytes. This is still high, and we feel we can improve this with lots of optimization. So the high runtime of our DKG is due to the computation cost of ACSS phase that we use. For low threshold, we use this ACSS from our CCS paper, and for high threshold, we use our new ACSS protocol. And here, the computation cost, if you see with high threshold, with n equals to 64, the computation cost of ACSS itself is like 125 seconds, and that's why we get 150 seconds of runtime, because the ACSS cost takes longer and the remaining costs are reasonably efficient. So in summary, we have a new ADKG protocol with communication cost of kappa n cube and computation per node, worst case computation order n cube, but in practice we see order n square for some technical reasons. We also have round complexity of order log n. We also have a new homomorphic high threshold ACSS scheme. Our implementation is the first asynchronous DKG implementation. There are lots of open problems. Again, one crucial open problem is to improve the high threshold ACSS scheme, because that's kind of the bottleneck in our DKG protocol. And also reduce the worst case round complexity to order 1. There are some theoretical ways of doing it. If you're interested, I can talk about it later. But I would like if there are some cleaner ways of getting these results. And also reduce the worst case computation cost to order n square. Now, in practice, we see order n square, but in the worst case, it can still be order n cube. And also, for ADKG, we don't know lower bound results, and it will be interesting to see if we can get some lower bound results for our paper, for ADKG primitive in general. And also, one of the interesting problem would be to implement it in like a more robust and multi-threaded way and see what will be the actual performance. And again, here are a list of my collaborators, and Ling is also here. If you have any question, you can ask me or my advisor, and thank you again.
Okay, thank you, Sourav. And again, we have time for a few questions.
Thanks for the talk. It's just to clarify, so the log n round time comes from the fact that you need to wait for these Byzantine agreements to finish, and each one takes expected constant. But
yes, yeah.
Okay. So can you break down the communication in cube, like which piece comes from which component? Why is there
The communication product.
like which piece contributes to the n cube complexity?
So now here, all the pieces, even these, each ACSS is n square, so we run n ACSS in parallel, so it's n cube. Even each RBC is n square, so n RBCs. Similarly, ABAs, each ABA is n square, so we get n cube. So it seems really hard to me that we can get beyond this n cube bounds, but I don't know any lower bounds as well. Yeah.
Thank you.
Okay, any more questions? If not, we are done with the first to talk. Thanks a lot, Sourav.